So welcome to today's session of the Discrete Maths 2 course. That's course session number 16 and the week 8. What we're going to do today is to finish our discussion of rotations, matrix transformations, and then we will move on to having a look at vectors, which is something that we have already seen. But over the next couple of course sessions, we are going to look at vectors from a geometric perspective, and we are going to see how we can write down equations for lines and planes. Before we do all this, you know what I'm about to do. I'm about to show you a question from our friend Dr. X, and this question has got to do with linear transformations, so that we don't forget what we are about to say. So we got a linear transformation. It's this function f over there. It goes from R2 to R2. And Dr. X says that if you feed that transformation with the vector 4, 4, you get the vector A2 as an output. If you feed it with the vector 0, 1, you get the vector 1, 2. Now, in case you're wondering what these T's are doing here, T stands for transpose. Fantastic. It's just so that I can write the vectors and they don't take up too much space. So I write them horizontally rather than vertically, so I can fit everything in one slide. Now, the question is, what is the value of f of 1, 0? So I've told you what f does to 2 points. But based on this information, you can use your Sherlock Holmes skills to figure out what f does to the vector 1, 0. Now I say Sherlock Holmes skills because this sort of indicates that, first of all, the answer is 1, elementary, Dr. Watson. So it's elementary. It's easy if you know your linear transformations. And second, it means that you don't need to guess anything. All you need to do is think logically. That's what Sherlock Holmes supposedly does all the time. And if he can do it, he was not even a computer scientist. Perhaps he was, we don't know. Certainly in spirit he was. Okay, so let's see. There have been already a couple of suggestions here. So let me write what we know. So we have that this is f of 4, 4 is A2, I seem to recall. A2, and f of 0, 1 is 1, 2. You can't see anything. So just a second, I'll try to fix that. Okay. So, yeah, that's not what I was trying to do. I was trying to do this. And let's get back to cinema mode. Perhaps you can see a little bit more. So that's what we got. That's the information that we got. And the question is, what is f of 1, 0 equal to? And I think I got a couple of suggestions. One of them was 1, 2, I believe. The other one was 2, 1. Well, let's see. Let's see which one it is. So now we got some scratch pads, so we can calculate. So how would you go about solving this exercise, this problem, answering this question that Dr. X asked? Okay, so you know that f of 4, 4 is A2. So What is f of 1, 1? Okay, so if you take 4 times 1, 1, you get 4, 4. F is linear, so f of 4, 4 is 4 times f of 1, 1. F of 4, 4 is 8, 2, so you need to divide that by 4. Because since f is linear, for every vector you know that f of ax, where a is a number, is a times f of x. Remember, that's one of the properties the linear functions satisfy. So f of 1, 1 is actually 2 a half, perhaps. The question is why? Because f of 4, 4 is 4 times f of 1, 1. Because of the property that we have here. Because 4, 4 is 4 times 1, 1. So f of 4, 4 is going to be 4 times f of 1, 1. So since f of 4, 4 is a 2, to get f of 1, 1, you just divide by 4 both components of the vector. So that's only logical thinking, as Sherlock Holmes would say. Use the data and the properties of linear functions to get f of 1, 1. And now we are in business. Why is that? Because there is another property that linear functions satisfy, and it has to do with addition of vectors. If you want to know what f of x plus y is, what is it that you need to compute? F of x plus f of y. Well, what is 1, 1? 1, 1 is 1, 0 plus 0, 1. Is equal to f of 1, 0 plus f of 0, 1. That's just linearity. We just use the fact that sort of linear functions behave very nicely when you apply them to sums of vectors. Now we know what this thing is. It's given to us. Well, we just figured it out. Actually, it wasn't given to us. It's 2, 1/2. We also know what f of 0, 1 is. It's 1, 2. So all we need to do to figure out what f of 1, 0 is just to subtract the vector 1, 2 from both sides. So f of 1, 0 is nothing but 2, 1/2 minus 1, 2. And that's 1 minus 3/2. Now, what matters are not the calculations. What matters is the way we went about solving the exercise, solving the problem. Exercise is a very weak word. So we had a problem that we needed to solve. We solved it. How? By using the definition of linear function and the data that we had available. If you just use the definition and the data, all you need to do is a few logical steps, you get the answer. And even the calculations, even though I may get them wrong, you won't get them wrong because they are not mind-boggling. Not in these examples, at least. Any doubts about what we've done to answer this question from Dr. X? The two key points are the two properties of linear functions. And you know this guy down there, even if he's pretty small? Luke Skywalker, yeah. He's named after me. Not really, no. Luke is just Luca. It's the same. We just happen to share the same name. Unfortunately, I'm not a Jedi warrior myself. Even though sometimes a lightsaber could turn out to be useful when I have to dodge bullets coming from students. It doesn't happen very often, but it can happen. The message is that, as Luke Skywalker would tell you, don't underestimate the power of the Force. And what is the Force here is knowing the basic definitions in the course. The only thing that you need to solve that exercise is to know what a linear function is. The rest is history. Well, the rest is just logical thinking, which you can do because you're masters at that. You're master programmers. There's nothing more logical than doing programming. Forget about mathematics. Mathematicians hand wave. Computer scientists can't because this thing doesn't understand hand waving. Okay, so thou shalt know your definitions. So unfortunately, fortunately or unfortunately, let's leave Luke Skywalker to ponder about linear functions and the power of the Force. And let's connect to what we were doing last time around by the end of the lecture, when we had a good laugh, where we finally could understand an SKCD comic. It doesn't happen very often. Sometimes I sort of stare at them, and after 3 years, I still don't understand why I should laugh. We continue again looking at linear transformations, but these are linear transformations that have to do with implementing some transformations in computer graphics. We saw last time how to implement rotations using a matrix multiplication. So just so that you can refresh my memory of transformations matrices, suppose that I want a matrix that implements a transformation that goes counterclockwise by t degrees. Okay, some people are looking for their visual memory. So what is the matrix? You take the cosinus of t minus the sinus of t here, and then you have the sinus of t here, and then the cosinus of t. That's the transformation that you can use to implement the rotation of points by t degrees counterclockwise by means of a matrix multiplication, which is nothing but applying a linear transformation, namely the linear transformation induced by this matrix. Now, suppose someone, for instance me, asks you to devise transformations that do these three things to an object. You first have to double the size of the y component of a point. So you have point xy, you double the y component. Then you take the reflection of the resulting vector on the x-axis. And then you rotate whatever results by 90 degrees counterclockwise. Okay, so let's try to do that. So the first thing is, was there smoke up there? The first thing is, let's double the size of the y component of a vector. I hope I'm not frying anybody's brain here. So and I also hope that nobody's frying anything up there because I'm hungry. Anyway, so double the size of the y component. That was step one. So what I want is to double the size of the y kid. I want a transformation T such that T of xy goes to x times x2y. Transformation T1. I don't know, perhaps this is running out of ink today. It looks like it was sort of weakish. Yeah, then I need more. Let's so what is the matrix? That induces this transformation? Okay, your colleague is saying 1, 0, 0, 2. And I don't think he guessed it. Why? Because you don't need to guess it. How do you find the matrix inducing this transformation once I tell you the formula for the transformation? I give you the specification of the function. Why is the first column 1, 0? Because if you actually apply the transformation T1 to the vector 1, 0, you get 1, 0 back. The second column is 0, 2, because if you apply the transformation to the vector 0, 1, that's exactly what you get, 0, 2. It always works like this, at least for transformations from R2 to R2. Always apply the function to the columns of the identity matrix of the appropriate size. And what is the appropriate size depends on the domain and codomain of the transformation. Okay, so that was step one. How about step two? Step two said, take the reflection on the x-axis. So let's implement that. Step two is by a transformation T2 that takes xy and maps it to x minus y. That's exactly the reflection on the x-axis. For instance, you take the point 1, 1, and you map it to 1 minus 1. So what is the matrix? Okay, we do exactly the same thing as we did before. We ask T2, if I feed you with 1, 0, what do you give me back? 1, 0. If I feed you with 0, 1, what is it that you give me back? 0 minus 1. So that's the matrix that induces this transformation. Finally, step 3 was rotation counterclockwise by 90 degrees. That was the transformation that we called last time R90, rotate by 90 degrees counterclockwise. And here, all we need to do is just to consult our visual memory. In this case, T is 90 degrees. So what is it that we get? Let me help you. That's the circle. And remember the cosinus, sort of this is a circle of radius 1. The cosinus is the projection of a point. The projection of a point on the x-axis, and the sinus is the projection of a point on this half circle in this case, because I didn't want to draw the rest. I don't need it right now, on the y-axis. So if I take this point, which is 1, 0, and I rotate it by 90 degrees counterclockwise, where does it go? It goes to 0, 1, because it gets here. So that's where it goes. So 0, 1 here. 0, 1. Instead, if I take 0, 1 and I rotate it by 90 degrees counterclockwise, where does it go? It goes to the green point. And since this is a circle of radius 1, the coordinates of this point are going to be -1, 0. So that's the third matrix that does the rotation for us. In fact, we did it. We saw this matrix last time around. So for this specific case of 90 degrees, we don't really need much trigonometry in order to figure out what the matrix is going to be, because the rotation is by 90 degrees. It's easy to see where points go to. So suppose now you want to apply these three transformations. One thing that you can do is to apply them to a vector one after the other by first multiplying the vector with the matrix A, then you multiply the result with the matrix B, and finally you multiply the result by the matrix R90. And this tells you where every point is going to go to. But in reality, do you need to do that? Or is it enough to apply only one matrix multiplication? And if so, by which matrix? Absolutely. Your colleague is saying what we are doing is the composition of three transformations. And since function composition at the level for linear functions is implemented by multiplying the corresponding matrices, the matrix that actually does the three transformations in one go is nothing but R90 times B times A. That's absolutely what it is. So you do R90 times B times A, and this thing is going to be a matrix that maps every point that you care to transform, xy, to where it should go. I encourage you to do this at home and see what happens to points. Do both the transformations one after the other and see that this matrix does exactly in one step what the three transformations do when applied in a sequence. Question? The question is, does the order of the multiplication matter in this case? That's a good question. I will need to check. In general, it does, but so whenever you run a matrix multiplication, you know order matters. I will need to check. I'm not geometric enough to figure that out off the cuff. I'm a more algebraic guy myself, so I will need to. Okay, so if one of your colleagues is saying the scaling might matter here, perhaps you're right. But in any event, it's not a complicated calculation. Try it. The message here was not the calculation, but the fact that since matrix multiplication implements function composition, you can actually do all these three steps in one go by using a matrix, which is the multiplication of the three matrices that describe each of the individual steps of the transformation. That's a message. Composition of functions, linear functions, equals matrix multiplication of the matrices that induce those functions. So matrix multiplication is your friend in more ways than one. So far, so good. Any doubt about what we've done? No. Oh, by the way, if you think that I'm going too slow, tell me to speed up. I can do that too. It's just that I'm not obsessed with the amount of material that I cover. I very much prefer that what we cover, we understand. But if you prefer to have a lot of stuff, I can give you more stuff. So let me close this discussion, this very introductory discussion of matrix multiplication and trigonometric functions with two useful but, let me say, infamous identities. These are the so-called sum rules of trigonometry, and when I saw them first time myself, I got squeaky bums, sort of, because they look so horrendous and complicated, and it looks like I need to remember them, and nobody wants to remember too many things. We got much more important things to remember in life, isn't it? Like your boyfriend's birthday or whatever. Okay, so these are two rules that tell you how to compute the sinus and the cosinus of t plus u, where t and u are angles, in terms of the sinus of the cosinus of t and u, the two angles. You know what? Dr. X asked me before I came here, gee, what are those? How can I remember them? And why are they true? Well, you know what? You can show Dr. X why they are true, because there is a very simple proof of why these formulae are true using matrix multiplication and rotations. So let's do it. In fact, I told him, with the people in the audience, with the help of the people in the audience, I'm pretty sure I can convince you that you don't even need to remember this stuff. The only thing you need to remember is that these are formulae that tell you that rotations can be performed one bit at a time. So why is that? Okay, so let's see this. So suppose that I want to rotate by my angle t plus u. And I think perhaps, if you don't mind, I'll try to get the fine pen back. Hopefully people can read it, and then we see. I actually prefer the thick pen, but I would need a larger writing space here. Okay? So what is the matrix that actually induces this transformation? Well, we saw it before. This is the cosinus of t plus u, cosinus of t plus u here, sinus of t plus u, minus sinus of t plus u. Those formulae that we had before, they basically told us expressions for this guy and this guy. Now, suppose that you want to rotate an object counterclockwise by t plus u degrees. Well, one way of doing that is to first rotate it by t degrees, and then you rotate it by u degrees, isn't it? So, pictorially, here I have my thing. Here I have my unit circle. Sort of, you can abstract the fact from the fact that I'm not Giotto, and so these are t degrees, and then I add u degrees here. So one thing that I could do is to start from here, and I first rotate by t degrees, and then I rotate the result by u degrees. Overall, I have rotated by t plus u degrees. How can I implement these two rotations? By means of a matrix multiplication. I know what is the matrix that induces the rotation by t degrees, and I multiply it with the matrix that induces the rotation by u degrees. First rotate this much, and then you rotate a little more. So what are these two matrices? Together, this composition would implement exactly this rotation that I have here by t plus u degrees. Do you agree with that? So what is this multiplication? Multiplication of two matrices. I said, and in this case, actually, the order of the matrix multiplication does not matter, because you could do the rotation in either order. You will still have rotated by t plus u. So let's say I first rotate by t according to my picture. I have cosinus t minus sinus t here, cosinus of t here. That's the rotation by t degrees implemented by means of this matrix. And here I have a matrix that does exactly the same for u degrees. So I have cosinus of u, sinus of u, minus sinus of u, cosinus of u. So let's do this multiplication, shall we? And see what comes out. I'll give myself a little bit more room. Okay, so what happens if I multiply? I take this row and this column. Okay, I get cosinus of t times cosinus of u minus, sorry, minus sinus of t sinus of u. That's the first component of this matrix. Because I multiply becomes cosinus of t. This gets multiplied by that. This gets multiplied by that. And the two get summed together. Okay, now I could actually compute the things that goes in here, but I don't care. It's not important to convince you that of the validity of the formula that I'm interested in showing you. What happens instead if I multiply the second row by the green column here? Well, I get sinus of u cosinus of t plus cosinus of u sinus of t. And of course, I could also compute what goes in here, but the fact is I don't care. It's not important for the thing I want to show you. What I want to show you is that the multiplication of these two matrices, which is this, which gives this result, is actually implementing the rotation by t plus u degrees. But this rotation is also implemented by this matrix that I have here. So these two matrices must be equal, because there is only one matrix that is associated with a linear transformation that induces it. We saw that last time round. But if these two matrices are equal, what does that mean? It means that they have the same elements in the same positions. So what? This thing here is actually equal to cosinus of t plus u, because that's the entry at position 1, 1 of this matrix. These two matrices are equal. This matrix number 1 is equal to this matrix number 2, so their first entries must be the same. And this entry here is nothing but the sinus of t plus u. But you know what? These are exactly the two formulas that we were staring at before, the so-called sum rules of trigonometry. If you don't believe me, look at the slide. You know, matrix multiplication and rotations just allow you to give a proof which is just really based on matrix multiplication and on the definition of the matrix that induces a rotation of why these two laws actually are true. There are many more complicated proofs and much more complicated proofs of this identity out there under the sky. I invite you, those of you who are interested in these kind of things, to look at them. But this is by far the simplest proof that I can think of. Unfortunately, it's not mine. Okay, so what these identities are telling you is that you can rotate by t plus u degrees by first rotating by t and then rotating by u, or the other way around. Any doubts about this? Okay, again, remember Luke Skywalker. Thou shalt not underestimate the power of knowing your definitions. Once you know that this is the matrix that induces rotation by t plus u, and that you can actually express this matrix as a composition of these two matrices, of the multiplication of these two matrices that describe rotation by t followed by rotation by u, then the proof is just a matrix multiplication, nothing else. Which is another one of the things that thou shalt know. The question is, does it also work if it's t minus u? Well, yeah, you can, but then you need minus u corresponds to a rotation clockwise. But yes, you can do that. You can come up with a formula for that case just by using matrix multiplication too. So you just move by t units in counterclockwise, and then you move back by u degrees clockwise. Excellent question. Thank you. Okay, so with this example, we are going to close our discussion of matrix transformations and how they can be used to implement operations in computer graphics. What we are going to do after the break, because we are going to sort of stick to the world of geometry, but we are going to look at our good old friends vectors from a more geometrical point of view. And this will lead us to re-examine geometrically some of the operations that we already know and love about vectors. For instance, what does it mean to sum two vectors geometrically? What does the inverse, the -1, of a vector mean geometrically? What does it mean to multiply a vector by a number, which is called a scalar in linear algebra? And how can we write equations in general for lines and planes in 2 and 3 dimensions? Well, these are the kind of topics that we will look at after the break. Any questions?
So, no.
Okay, no questions. So we reconvene in 10 minutes. 13:10 to be precise.